Hi, my name is Alexis, and today I'm going to talk about the analysis of variance, which is ANOVA in SPSS, or introduction. So, what is actually ANOVA? ANOVA is a test, is a way to find out if a survey or experiment result are significant. In other words, they help you to figure out if you need to reject the new hypothesis or accept the alternate hypothesis. So basically, they test groups to see if there's a difference between them. For example, when you want to test the difference group, like a group of physician patient are trying to three different groups, like counseling, medication, or biofeedback. So you want to see if one therapy is better than another. Another example is students from different colleges take the exam, I mean the same exam. So we want to see the result of each college and their performance. And this is what the data we're going to use today. We have gender, which has two levels, male and female. And for the subject, we have three levels, English, science, and mathematics. And we also have score for the group. And this is how the data looks like after you import the data from Excel to SPSS. As you can see, the data is going to be the same, male, female in gender, and subject. We have English, science, and mathematics, and the score. And what actually is one-way and two-way means? So one-way ANOVA, it compares the means across one independent variable with more than two levels of groups. For example, one way, um, one way we have the gender, which has one independent variable. For example, we have gender, and in two ways, the definition is it extends the one-way ANOVA to two independent variables. It can explore the main effects of each variables and the interaction between them. For example, in two ways, it has two independent variables, and it can also have multiple levels. For example, in the data that we're gonna use, we have gender and subject. So in one way ANOVA is a statistics methods used to determine if there are any statistically significant difference between the means of three or more independent groups. And if you can see, it often referred to as only a factors, and the factor has three or more levels of group. Let's assume that there are no significant difference between the group. ANOVA calculates an F ratio, which compares the variance between groups means to the variance within the groups. So if the F ratio is statistically significant, it suggests that at least one group is different from another. If ANOVA indicates significant difference, post hoc tests are often used to identify which specific groups dif differ from each other. Okay, and two-way ANOVA, it extends one-way ANOVA by introducing a second independent variables, allowing for the examination of the effect of two factors and their interaction on a dependent variable. And you will have two independent variable, often referred to as a factor. Each factor has two or more level of groups. The main effect refer to individual effect of each independent variable on the independent variable. And the interaction effect explore whether the effect of one dependent variable on the dependent variable depends on the level of another independent variable. Like one-way ANOVA, in two-ways ANOVA calculates an F ratio. It assesses the significance of the main effect and the interaction effect. And post hoc tests may apply if there is a significant interaction effect or main effect to identify specific group differences. And this is the difference between the significant and non-significant. As you can see, um, in significant, there is no overlap between the significant group. And if you take a look at non-significant, there's actually an overlap in the middle between both groups. So right now, I'm going to demonstrate on how to conduct a one-way ANOVA using SPSS. So this is our file. This is SPSS map. And if you want to conduct it, go import data and click Excel. And this is where I store my data. Alright, so this is exactly how it looks like in Excel. Say okay. And yeah, so we have the gender, subject, and score. And you can see the levels, 2 levels, 3 levels, and the score. And right now we're going to test one-way ANOVA. We're going to compare means and proportion and click one-way ANOVA. Alright, so as you can see, we only have score. That's because um, in SPSS, they only allows numeric. So as you can see, this is like alphabet. So we want to transform them into numeric. So I'm going to do genders. Okay. And then we're going to do the same thing for subject. Right. Transform subject, put it back, and pick subject, and do rename it. You cannot rename the same thing, but you're just going to rename something else. And right now you can see we have genders and subject, and you can tell that male is indicate 2 and female is 1. Same thing for subject, English is 1, science is 3, and mathematics is 2. Cool. So right now we're going to go to analysis and test the one way ANOVA. Here we go. Now we have the data here. So scores is, I'm going to put it in independent list, and we're going to test subject. So in one-way ANOVA, you can only test one independent variable, but in two-way ANOVA, you can put more than one. So I'm going to put gender and subject in. And we're going into post-hoc, and sorry, it's not this one. Going to options, and we want descriptive and homogeneity of various tests, brown forcing tests, bush tests, means. And so this couple tests is actually in case we violate the homogeneity of variance test assumption. So, yeah, we want to make sure the level is in default 0.05. gonna click Turkey, right? And okay, so this is our test. Um, so if you can see in descriptive, you can see that in our data, the mean here is we have English 7.1, 7.1 and 0.75. And you can see that science, the mean of science is lower than, I mean, it's higher than English and math. And English is higher than math. So actually, mathematics is the lowest for me. And alright, in our test of homogeneity of variance, we can see that the significance is zero, I mean 0.052, which is higher than our default 0.05. So we can tell that 0.052 is greater than 0.05, so it is non-significant. And we have our ANOVA. So if our significance is at 0.001 level, looking at between the group 0.001, so that means that it is a statistically significant differences between the levels of the independent variables. But if we look at the post hoc test, we won't know the differences. So post hoc test, it won't tell us the differences. And if we look back, um, this in our significant point, we have 0.868. So what it means that 0.868 is a non-significant. How can you tell? Because it's it's bigger than 0.05, so it's a non-significant. And since we have our homogeneity variance test, homogeneity test right here, so we don't have to worry about the robust test of equity of means. And in our post hoc test, we just select Turkey just now. So if you can see that the data here, mathematics, science, I mean English, mathematics, and science, um, for the significance for this group, um, there is there is no significance between the groups. To determine whether any of the differences between the means are statistically significant, compared to the p-value to your significance level to assess the null hypothesis. The null hypothesis states that the population means are all equal. Usually a significance of 0.05, it works very well. Um, and a significance of level of 0.05 indicates a 5% risk of concluding that a differences exist when there is no actual differences. And this is the mean plots, and you can see that English is about 7.1, I mean 71.63, and mathematics we have, I mean mathematics is 71.63 and English is 71.75, and for science we have 75.86. So this table shows the mean for the subject. And right now we want to use the general linear model. If we go back analysis, general linear model, uni univariate, and we want to put score for dependent variable and subject for our fixed factors. Okay, and if we go options, we want to put descriptive statistics, the estimate of effect size, and observed power, and homogeneity test. And we want our significant level to be 0.05. Continue. And for our post hoc test, we want to have subject and we select Turkey. And for the plot, we want to put subject and just add it and continue. Click OK. And this shows our test result for univariate analysis of variance. And this is the result of using the general linear model, and they are just different data available. So if you look at between subject factors, you can see the subject for the n, which actually means the size of the subject for English, mathematics, and science. And in Liew test of equality of error variance, if so we can see that is zero, I mean for 0.052, which means that is larger than 0.05. So it tells us that it is a non-significant, and is actually 0.052 is actually the same as, if you scroll up, for our test of homogeneity of variance is the same. If you can see here is 0.052. Okay, and for our post hoc test, we can see that the STD errors, they are all almost the same. And if you scroll down for our profile plots, you can see that they are exactly the same as above. So this shows that the plot that represent the means of each level of variables. And now I'm going to show you how to conduct a two-way ANOVA by using SPSS. And so we have two independent variables, the gender and subject. And now you may be wondering why t-test couldn't use for our data right here. And well, because there are a few reasons. First of all, our subject has three levels: English, science, and mathematics. And the t-test will only allow two levels of independent variable, although you could certainly run a t-test for every possible combination. For example, a t-test between mathematics and English, or English and science, or t-test between the scores, mathematics, and English. In general, you can only have two levels, and but there are still other difficulties with the t-test for this type of data sets. First, running multiple t-tests, it will increase the type 1 error. So the probability that we will reject the null hypothesis when in fact it was true. So using an example like this, we may find, let's say, the level between male and female, the two level of the gender independent variable may find that there are statistics significant between the score, male and female, and we would reject the new hypothesis that there was no differences on the score level variable between the two independent variable. But in fact, there was no differences, so that's a type 1 error. We would be saying we are rejecting the null hypothesis. We'll be saying that there will be no differences when in reality there is no differences when you run multiple t-tests. So you increase the chance of making a type 1 error, also known as the alpha error. Secondly, the multiple t-tests, we cannot study the interaction effect, and this is really one of the greatest feature of ANOVA. We can look to see if there's an interaction effect between subject and gender. We would call that subject times gender. So subject going to times the gender. So the main effect will be with one independent variable, and the main effect of the subject on the dependent variable, which is the score, is the main effect of gender on the independent variable. But ANOVA allows us to look at the interaction effect between subject and gender on dependent variables. So let's run the analysis of two-way ANOVA. So first of all, we want to go to analysis, and we're going to click general linear model, univariate. All right, so it's the same thing. We're going to put score into the dependent variable, and gender is going to be the fixed factors, and subject is going to be in the fixed factors. This is what's special about the two-way ANOVA, that you can put two independent variable. Now for the post hoc test, in this example, it won't work for gender because it has only two levels, male and female. So there is no need for post hoc test for the gender, but for the subject, we can click in here. I mean, subject, and you could have one subject and select REGWQ for this post, because when samples size are similar, this post hoc test offers a good control of type 1 errors and also good power for the ability to detect a differences when it is there. And the next one, we want to go to EN means. I will display the means for overall, gender, and subject. And we want to have the gender and subject. Of course, we want to compare the main effect. And from here, I want to change this to Bonferroni and click continue. And I do want to, yeah, I do want to click the options, and I want to choose uh, descriptive statistics to display this guy, and estimates of effect size and homogeneity test. And the default, I'm going to set this to a significant of 0.05. And that's it. I'm going to click OK. And this is the result. And moving on, we have the descriptive statistics. And here, fairly straightforward. You can take a look at the means. And if you can see the subject, we have English, the means is 77.25, mathematics 70.80, and science 79, and that's for female. And the male, we have English 66.25, mathematics 73, science 73.50. And if we move down, we have the Liew test of equity of error variance. And so a question for you is, are you going to reject the new hypothesis? No. Let's take a look. Because here we have the mean 1.71, and that tells us that 1.71 is larger than 0.05. If the significance is lesser than 0.05, then we will reject the null hypothesis. This is something that you have to declare as limitation in manuscript if you are going to include this result in the manuscript. But two-way ANOVA is fairly robust to violating this assumption and the assumption of homogeneity of variance. So it is not something that I'm going to stop the analysis, but something that can certainly I need to be aware of. And if we move down, we have the test of between subject effect. You can see that we have subject is a statistically significant between the dependent variable subject and the subject level for the independent variable, which is the subject is statistically non-significant. You can see it's 8.870. So it's a non-significant because it is greater than 0.05. And if we take a look at gender times subject, and that is also not statistically significant, and the partial 8 square is 0.029. So 0.029 of the score can be explained by the gender times subject larger than subject alone. So you can see 0.029 is larger than subject. And we're moving on, we can see the grand mean. And we have the result for subjects level, and we have the estimates. Now we have the estimates for the subject, and again, what stands out here is the means for a subject group. Moving on, we have we have the pairwise comparison. So we know that there is a statistically significant differences between the level of subject and dependent variable on the subject level, like unit tests. And if we look down, we can see that the subject times gender. So this is the interaction effect of subject times gender. We can see that again. We just look at this really quickly. It seems like the gender times subject, it gives us English, we get 77.250, and when female times mathematics, we get 70.800, and female times science, we get 79.000. And for gender male, when it times English, we get 66.250 for the mean, and for mathematics, we get 73. And when male times science, we get 73.5000 for the mean. And we can tell that science have the highest than English and mathematics, and the lowest gonna be mathematics. And for male, we have science the highest. And if we scroll down, this is actually the result for REGWQ test for the homogeneous subset. So you can see that the subset that we have, they are all in the one, just in one subset for English, mathematics, and science. And If we look down here, you can see that the profile plot. So this is the gender. You can see that the mean score for the female is higher than the male. And if we look down here, we can see that each subset compare to all the subject here. We can see that English is fairly about 71 something, but mathematics is higher than English. But we can tell that science is the highest between English and mathematics. And if we look down to the last plot, and we can look at them combined. And again, before I analyze this graph, just want to note that this fictitious data, so this data that was just made up used for this analysis, but if this were a real data, I will show you how this will be interpreted. So you can see that both male and female in the each subset, you can see that English is the blue line here, and mathematics is the red line, and science is the slightly green line here. And you can see that female is for the female is for the score for mathematics is the lowest and English is higher, but the highest is science. But male, you can see that science and mathematics they are super close here, but English is way down here. So English is the lowest. And you can say that you're trying to apply the findings just to interpret female result. We can say that English, mathematics, and science, the female results for all three subjects are not equally close because there's a huge gap compared to the male. And but for male, we can see that mathematics and science are equally close but not English. So overall, when we interpret this result and trying to apply them using all three levels, you might say female have more benefits, the most in three subjects, and the male, all this information, of course, as indicate in the table, which shows above, but I feel like it's always good to have the graphical representation as it helps in the interpretation of the result. And this is how a way on how you conduct a two-way ANOVA based on our data. And this is the end of my video, and I hope you enjoy my presentation, and I will see you soon. Thank you.